So here, same as before, maintain a linked list, subject to insert a node at this location, delete a node at this location, and order queries. Is node X before node Y in the list? This is what we needed to support full persistence. So you have a big linked list. And then if I give you this node and this node, I want to know that this node is before that node in the list in constant time. I claim that we can solve this problem given our solutions to list labeling. Not so obvious how. List labeling is great because it lets you do order queries, right? You just compare the two labels and you instantly discover which is before which. And so if we could afford log n time over there, we could just use this solution, and this is reasonable. But we really want constant time per operation. Now if we do constant time per operation, and we use exponential label space, this is not so good because it means you need n bits to write down a label. So it's going to take like linear time to modify or to compare two labels. So you don't really, this doesn't save you. We can afford to do this. This is only log n bits per label, and we assume all of our integers can store at least log n bits. This is something called a word RAM model. And so we can afford to store these labels, but we pay this log n time. So we've got to remove a log n factor. How do we do that? Indirection, just like last class. Okay, so let's do that on this board. So on the top, we're going to store n over log n items using this list labeling with label space, say n squared. Any polynomial will do. And so this takes log n per operation to do anything on these n over log n items. And then at the bottom, we have lots of little structures of size log n. And that's supposed to eat up a factor of log n in our update time, if we do it right. OK. Actually, I can just do list labeling down here as well. So if I'm only storing log n items, then I can afford to use the exponential solution, the trivial thing where I just bisect all the labels until all the log n items have changed, then rewrite them. Because 2 to the log n is only n. So here, in each of these, I do list labeling with space 2 to the log n, okay, also known as n. So these guys are constant time to do anything in, to maintain the labels. And to maintain the labels up here, so to maintain basically each of these n over log n guys is one representative element from, or representing this entire group. There's n over log n of these groups. So this label structure is supposed to distinguish the different groups, and then the labels in here are distinguishing the items within the group. Now this costs log n amortized to keep what we need up here. But now if I want the label of an item, I just take this label, comma, this label. So if I have an item here, for example, I store, first I look at the label of this block as stored by this data structure, and then I look at the label within the block. And so my composite label is going to be an ordered pair of top label, comma, the bottom label. Okay, this is kind of funny because it looks like we're solving the list labeling problem again. with now a space of n cubed. Right? We've got n squared for the first coordinate, and then n for the second coordinate. So if you just concatenate those two labels, that lives in a bigger label space of size n cubed. And yet I claim this takes constant amortized and is not a solution to list labeling. It's just a matter of again, how updates are performed. With ordered file maintenance, we had to physically move items. With list labeling problem, we had to modify the number stored with each node. That's expensive. In this world, if we change a label up here, we are basically instantly, say we change the label corresponding to this group in here. We change the label of all of these items in one operation. Or actually, it takes log n time, and then we change the label of all log n of these items. So that's why we get constant amortized. So how does this work? If we insert a new item, we stick it into one of these blocks, the block that it fits into. If this block gets too full, more than, say, 1 times log n, then we split it in half. If it gets too sparse by deletion, say less than 1/4 log n, then we'll merge it with one of its neighbors and then possibly split. Each of those triggers a constant number of operations up here. And so we pay log n, but we only pay it when we've made theta log n changes to one of these blocks. So we can charge this log n cost to those log n updates. And so this turns into constant. This down here is always constant. And so it's constant amortized. And if each of these blocks remembers what the corresponding, and basically this is a linked list here, and then we have linked lists down here, and they have labels. And so it's like a what do you call a skip list with just 2 levels. And every node here just remembers what its parent is up here. So if you want to know your composite label, you just look at the bottom label and then walk up, look at the top label. Those are just stored right there in the nodes. And so in constant time, you can find your top label, your bottom label. Therefore, you can compare 2 items in constant time. So this solves the problem we needed in lecture 1. Question?
Sorry, why doesn't it save as n cubed?
Okay, why is it not the same as n cubed label space, which I claim has a lower bound of log n? The difference is with list labeling, you have to explicitly change the label of each items. And here, we're basically computing the label of a node now becomes a constant time algorithm. We're allowed to look at the label here, then walk up, then look at the label here. And by changing the label up here, we change it simultaneously for log n guys down there. So that's the big difference between this list order maintenance problem from the list labeling problem. These were actually all solved in the same paper by Dietz and Slater, but sort of successively slightly relaxing the problem makes a huge difference in the running time you can achieve. Obviously, we can't get any better than constant, so we're done. Of course, then there's external memory versions, but in terms of regular data structures. And again, Willard made it worst case constant. That's a lot harder. Other questions? Cool. So that does ordered file maintenance and list labeling. And so next we're going to move to a very different data structure, which is cache oblivious priority queue. We haven't really done any cache oblivious data structures yet, so it's time to return to our original goal. We're not actually going to use order files, sadly. That was last lecture. So all of this was continuation of last lecture. Now we're going to do a different data structure. It's going to adapt to B, it's going to adapt to M, it's cache oblivious, and it achieves priority queue. Now, remember this sorting bound, n over b, log base m over b of n over b. This is our sorting bound. Then the priority queue bound we want is this divided by n. So we want to be able to do 1 over b, log base m over b, n over b, insert, and delete min, let's say. And this is an interesting bound because it's usually much less than 1. It's a subconstant bound. This is going to be little o of 1, assuming this log is smaller than this b. So it's little of 1 if, let's say, b, or yeah, I guess b is bigger than log n, roughly. This would in particular be enough. No pun intended, be enough. So if our block size is reasonably big, cache line is bigger than log n, which is probably most likely in typical caches and architectures, then this is more like 1 over b, never mind the log. And so we have to do b operations in one step. And then to really get the log right, we have to depend on m, not just b. Okay, now, as I mentioned, that's the bound we're going to achieve. We do need to make an assumption about m and b and how they relate. So we're going to assume a tall cache, which is m is, let's say, b to the 1 plus epsilon. So it has to be substantially bigger than b, not by a huge amount. Could be b squared, could be b to the 1.1 power. But m is definitely at least b, and I want it to be a little bit bigger. I want the number of blocks to be not so tiny. Okay, then here's how we do it. I think I need a big picture. So the kind of funny thing about cache flow-based priority queues is we're not going to use trees. It's basically a bunch of arrays in a linear order. In some ways it's an easier data structure, but it's definitely more complicated. But hey, it's faster than B trees. If you don't need to be able to do searches, you just need to be able to do delete min, then priority queues are a lot faster than B trees. Okay. Draw this. I want to try to draw this pseudo-accurate size. The only part that's inaccurate about this picture is the dot, dot, dots. Lets me cheat a little. Okay, so we have x to the 9/4, x to the 3/2, and x. Okay, this is sort of what the levels are going to look like. So we have a linear sequence of levels. They are increasing doubly exponentially in size. Right? If you look at what's going on here, doubly exponential. It's supposed to be this. So this is the top level, and this is the bottom level. Okay, so at the top we're going to have something of size n. And at the bottom, we're going to have something of size c, constant. And what I've drawn is the generic middle part. So we go from x to x to the 3/2 to x to the 9/4. Or you could say x to the 9/4 down to x to the 3/2 down to x, according to this exponential geometric progression, I guess. So that's how they go. So if it was just exponential, it would be like n over 2, n over 4. But we're doing, in logarithms, we're changing by constant factors. So it's doubly exponential. And then each of the levels is decomposed into top buffers and up buffers and down buffers. Okay, and as you see, the size of the top buffer is equal to the sum of the sizes of the bottom buffers. So let me elaborate on how this works. So level x to the 3/2. So we're going to generically be looking at x to the 3/2. So I can easily go down, that's of size x, and up is x to the 9/4. Easily. There's always one up buffer of size x to the 3/2. So maybe some color. So this buffer here is x to the 3/2. And then we also have up to x to the 1/2 down buffers. Each of size theta x. So each of these guys has size theta x. And then the number of them is at most x to the 1/2. And so you take the product, that's x to the 3/2, which is the same as the up buffer. Okay, so that's the way this cookie crumbles. That's how each of these guys decomposes into little pieces. And so in particular, this up buffer, if you work it out, should be exactly the same size as this down buffer. Maybe it's easier to do these two. So this down buffer has size x. And if you have a structure size x, the up buffer has size x, right? X to the 3/2 has an up buffer size x to 3/2. So this will be size x, and so these match. These are equal size. That's why I drew it this way. Okay? Now, the dot, dot, dot hides the fact that there are x to the 1/2 of these. So there's a lot of down buffers. They're actually a lot smaller than up buffers. But these two match in size, and these two match in size, and so on. Okay. Okay, there's a small exception. I'd put theta x here. The exception is that the very first down buffer might be mostly empty. So this one is not actually theta x. Each of these will be theta x. And this one over on the left will be big O of x. Okay, small typo in the notes here. So if that's not sufficiently messy, let me redraw it, make it a little cleaner. I want to look at two consecutive levels and specify invariance. So after all, I'm trying to maintain a priority queue. What the heck is this thing? Okay, the idea is that towards the bottom, that's where the min is. That would seem good. Because at the bottom, you're constant size. I can diddle with the thing of constant size if it fits in a block or if it fits in cache. It takes me 0 time to touch things near the bottom. So as long as I always keep the min down there, I can do find min in 0 time. And delete min will also be pretty fast. I'm also going to insert there because I don't know where else to put it. I'd like the larger items to be near the top. I'd like the smaller items to be near the bottom. But it's kind of hard to know when I insert an item where it belongs. So I'll just start by inserting it at the bottom. And the idea is as I insert down here, things will start to trickle up. That's what the up arrows mean, that these items are moving up. And then down arrow items are items that are moving down. Somehow this is going to work. So let me tell you the invariance that will make this work. If you look at the down buffers, they are sorted. Or I should say all the items in here are less than all the items in here, and so on. But within each down buffer, it's disordered. Okay, then we also know this. All the items in the up buffer in a given level, this is x to the 3/2, let's say. And this is x. All the up items are larger than all of the down items. So that's like, I mean, it's just an inequality here. Okay, so these guys are basically in a chain. Again, the items in here are not sorted, but all the items here are bigger than all the items here, bigger than all the items here, bigger than all the items here. Now, what about from level to level? This is a little more subtle. What we know is this. So again, we know that all the down buffers are sorted, and we know that this down buffer, all these items come before all this down buffer items. But these up buffer items, we don't know yet because they're still moving up. Now we know this. They need to move up, but we still don't know how far up. We don't know how these items compare to these items, or these items could have to go higher. Could be they belong here or here, who knows. So basically the down buffers are more or less sorted, and so the mins are going to be down at the bottom. And the up buffer items, I mean, they're still moving up. We don't know where they belong yet, but eventually they'll find their place and start trickling down. Roughly speaking, an item will go up for a while and then come back down, although that's not literally true, it's roughly true. Okay. I should say something about how we actually store this in memory, because the whole name of the game is how you lay things out in memory. In Cache Oblivious, that's all you get to choose, basically. The rest is an algorithm, regular RAM algorithm. And all we do is store the items in order, say, from bottom to top. So store the entire C level, then the next level up. Just store these items as consecutive arrays. That's what we need to do. Leave enough space for x to the 1/2 down buffers, each of size theta x. Okay. So, how do we do inserts and deletes? Let's start with insert. As I mentioned, we want to start by inserting in the bottom until we run out of room in the bottom, and then things have to trickle up. So here's the basic algorithm. You look at the bottom level, you stick the item into the up buffer. This is not necessarily the right thing to do. So here, you stick it into the up buffer, but these things are supposed to be roughly sorted. So once you stick it there, you say, oh, well, maybe I have to go down here, go down here. The point is, the up buffer is the only one I want to be growing in size. So I insert into the up buffer, and I say, oh, potentially I have to swap down here, swap down here. I mean, this is constant size. I can afford to look at all the items here in 0 time and find out which buffer it belongs to. As I move the item down here, I swap. So I take the max item here and move it up to here, move the max item from the next down buffer and propagate it up so that I keep these things in order. Swap into bottom down buffers. If necessary, or maybe as necessary. Might have to do a bunch of swaps, but it's all constant. And then the point is, the only buffer that got larger by one item was the up buffer, because here we did swaps to preserve size. And if that overflows, then we do something interesting. And something interesting is called push. So this is a subroutine, which I'll define now. general, so this is the bottom level push, but I want to define the generic level push, which is we're going to be pushing X elements into level X to the 3/2. So why is that? Check it out. If we're at level X and our up buffer overflows and we're trying to push into the next level, that's level X to the 3/2, then the push, the up buffer that we're trying to push has size X. So the up buffer has the same size as the level name. So if we're at level X, this has size X. We're trying to push X items up into the next thing. Okay, so this up buffer we're going to empty out the up buffer, send all those items up there. Cool. So what do we do? How do we do this push? First thing we do is sort the items. Those X items. This is where I need the black box, which is that we can sort in n over b, log base m over b, n over b, cache obliviously. So we're going to use that here. It's not hard, but I don't want to spend time on it. Okay, now the interesting bit is how we do the push. Okay, the tricky part is we have all these items. We know that they're bigger than all the items below them. Maybe here's the better picture. We know these guys need to go up. They're bigger than everything, all the down items below us. But we don't know, does it fit here, 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 or here? But we do know that these things are ordered. And so if we sort these items, then we can say, well, let's start by looking here. Do any of these items fit in this block? Just look at the max here. And if these guys are smaller than the max here, then they belong here. So keep inserting there. Eventually, we'll get bigger than the max, then we go here. Look at the max item here. As long as we have items here that are smaller than the max here, insert, 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 insert. And so on. And then when we're beyond all of these, maybe we're immediately beyond all these. We have to check, oh, bigger than the max, bigger than the max, bigger than the max. Then we put all the remaining items into the up buffer. This is called distribution. So we're looking at level X to the 3/2 and just scanning sequentially. Because we just sorted them, we're scanning them in order. We visit the down buffers in order. And insert into the appropriate down buffer as we go. Now, there's a little bit that can happen here. Our down buffers have a limit in size. Down buffers are supposed to have size theta x at level x to the 3/2. So as we're inserting into here, a down buffer might overflow. I've got theta slop here. So when a down buffer overflows, I just split it in half. I then make two down buffers, well, actually it'd be like here and right next to it. I'm going to maintain a linked list of down buffers. And each of them will have space for, say, 2 X items. But now, once I do a split, they'll both be half full. Okay, so when a down buffer overflows, split in half. And maintain a linked list of down buffers. Another thing that can happen is when you increase the number of down buffers, we have a limit on how many down buffers we can have, up to x to the 1/2 of them. So if we run out of down buffers by splitting, then we need to start using the up buffer. So maybe here we create, we split maybe this buffer. There's now too many down buffers total. Then we'll just take all the elements in here and stick them into the up buffer, because that's where they belong. So when the number of down buffers is too big, when that number overflows, move the last down buffer into the up buffer. Okay, so there's basically two ways that elements are going to get into the up buffer. One way is that we run out of down buffers, and so the last down buffer starts getting promoted into the up buffer. The other possibility is that we're inserting items that are just really big in value. And if the items that are getting promoted from here into the next level just happen to be larger than all these items, we will immediately start inserting into the up buffer. But in general, we have to look at this down buffer, look at this one, then that one. Okay, that is insert and push. I think before I talk about delete, I'd like to talk about the analysis of just insert and push. Keep it simple. And then I'll briefly tell you about deletion. So, oh, I didn't say, sorry. There's one more step, which is the recursion. Run out of room here. So maybe I'll go over here. This is nothing relevant. So I need to recurse somehow. In general, I'm at some point inserting things into the up buffer. The up buffer might overflow. That's the one last thing that could overflow. When that happens, I just push it to the next level up. Okay, so as we do insertions in here, we might start inserting a lot into here. Eventually this will get too big. It's supposed to have size x to the 3/2. If it gets bigger than that, take all these items and just recursively push them up to the next level. And conveniently, that's exactly the same size as we were doing before. Here we did x into level x to the 3/2. Next will be x to the 3/2 into level x to the 9/4, and so on. Always the size of the up buffer. So the claim is, if we look at the push at level x to the 3/2, which is what we just described, and we ignore the recursion, then the cost is x over b log base m over b of x over b. So sorting bound on x items. So we spend that right away in the very first step. We sort x items. So that costs x over b times log base m over b of x over b. And the whole point of the analysis is to show that this distribution step doesn't cost any more than the sorting step. So let's prove this claim. And the first observation, maybe don't even need to write this down. So remember, with cache oblivious B trees, we looked at a level of detail that was sort of the relevant one that straddled B. Now we have this data structure, and there's no longer recursive levels in this picture. It's just a list. But one of the things we said is that if you look at the very small structures, those are free because they just stay in cache. I'm going to assume, this is a little bit of a bastardization of notation, assume that all the levels up to m fit in cache. It's really up to like size m over 2 or something, but let's just call it all. If x is less than m, then all this stuff has size order m, and so let's just say, by redefining what m is by a constant factor, that just fits in cache, and because we can assume whatever cache replacement strategy we want, assume that these things stay in cache forever. So all of the bottom stuff, size up to m, is permanently in cache and costs 0 to access. So those levels are for free. So it's all about when we touch the upper levels. And really, the most important level will be the transition from the things that fit in cache to the next level up that does not fit in cache. That's going to be the key level. But in general, let's look at a push, or let's just assume x to the 3/2 is bigger than m. Okay, because we're looking at a push at level x to the 3/2. And I'm just, by definition, if it's less than m, it's free. Question?
So how can you assume that all of the things below that particular size always stay in cache? So you're making assumptions on the
I'm making an assumption on the cache replacement strategy, which I actually made last lecture. So I said magically assume that we use optimal cache replacement. So whatever I choose, opt is going to be better than that. So you're right. The algorithm doesn't get to choose what stays in cache. But for analysis purposes, I can say, well, suppose all these things stay in cache. If I prove an upper bound in that world, then the optimal replacement will do better. And the LRU or FIFO replacement will do within a constant factor of that. If you, again, by changing m by a constant factor. So I'm freely throwing away constant factors in my cache size, but then I will get that these effectively stay in cache. FIFO or LRU will do that just as well, or almost as well. Good question. Okay, so now we can just look at the pushes above that level. And I really want to look at this transition level, but we're going to have to look at all of them. So let's do this. Now, I also have tall cache assumption. M is at least b to the 1 plus epsilon. I actually want a somewhat bigger assumption, which is that m is greater than or equal to b squared. Okay, if it's not b squared, you have to change this 3/2 and 9/4 and stuff to be something a little bit bigger than 1. And it gets really messy to write that down. So this data structure with appropriate modification does work for other tall cache assumptions, but let's just assume this one. So this means m over b is at least b. That's sort of the clean statement. It's true for most caches also, but this will be my assumption. Okay, cool. So if we just do some algebra, claim is this is x is greater than b to the 4/3. So that's just taking this inequality, x to the 3/2 is greater than or equal to b squared, and raising to the exponent 2/3, and so this turns into x, and this turns into b to the 2 times 2/3, which is b to the 4/3. So x is quite a bit bigger than b. Okay, in particular, this means that x over b is bigger than 1. Okay, by a lot, but if we take ceilings on this, no big deal. So we don't have to worry about the ceilings. All right, now the claim is that the distribution step costs, this is really the interesting part, x over b plus x to the 1/2 memory transfers. Okay, why? Remember up here we have x to the 1/2 down buffers that we're looking at. And we're visiting them in order. We touch this down buffer. And really we just care about the max here. And then we start writing elements one by one. But if we write elements one by one, the very first element we write costs an entire memory transfer. We have to load in a block. But then we can fill that block and then write out that block. So we get to write out b items in one step. So we pay x to the 1/2 because we have to touch the last block of this down buffer, this down buffer, this down buffer, and there are x to the 1/2 down buffers. So each one we have to pay 1. That's this part. That's the expensive part. But then once we're actually writing items, if we stay here for a while, that's basically for free. Overall, we're writing x items, and so to write them all, we'll only take x over b ceiling sort of over the entire summation. But we have to pay 1 to start out here, here, and here. So this is like the real amount of time. And now I want to amortize that, essentially. Or actually, so there's two cases now. If x is greater than or equal to b squared, then we're happy. X is greater than or equal to b squared, then this term dominates. And so this is tinier. Right? Say x is b cubed. Then this is x to the 3 halves. This is b to the 3 halves. This is b squared. So this is bigger. And so then the cost is just x over b. And we're done, because we need to prove it's x over b times log. We had to do this to sort, but this distribution will be free. Now that says all the high levels are free. All the low levels are free, right? If you're less than b squared, then you're less than m and you're free. It's saying if you're bigger than b squared, you're free. But there's going to be one level right in between where you're not really bigger or smaller. So there's one level where it's going to be b to the 4/3 less than or equal to x less than or equal to b squared. I guess strictly less than. Okay, because you're jumping in this doubly exponential way, you might miss slightly. And so you're in between these two levels. Yeah. Why is this? Because we only know that x to the 3 halves is less than m. We don't know that x is less than m. So we have a bit of a slop there. So then, at this transition point, what we do is say, okay, we can't afford to store this whole x to the 3 halves is not less than m. So we can't afford to store all this in the cache. But we can afford to store the last block of this guy and the last block of this guy. All the down buffers, we can store the last block in cache. Why? Because there's only x to the 1/2 of them. And we know that x is less than b squared. So if x is less than b squared, x to the 1/2 is less than b, which is less than m over b, because m is at least b squared by tall cache assumption. So this is the number of blocks that we can afford in cache. This is the number of blocks we want. I want one block for each of these. So basically then, this x to the 1/2 term disappears for the one transition level. So this is free. So you can afford one block per down buffer in cache. And so again, we get an x over b cost. Okay, so the distribution is basically free. The hard part is the sorting. And then the idea is that, well, okay, now this is one push. When we do an insert, that item might get pushed many times, but basically can only get pushed once per level. So you end up taking this cost and summing it over all x. So if you look at an insertion, amortize what you pay, or you look at the sum over all these things. You get the sorting bound on x summed over x, where x is growing doubly exponential. And so this becomes a geometric series, or even supergeometric. And so you get, I guess I should look at it per element. If you look at the amortized cost per element, so I get to divide by x. So when I do a push, I push x elements. So I get to divide by x here. And then if an element gets pushed at all levels, I have to sum over all these x's. But you do this summation, and you get order. It's dominated by the last term. Sorry, this should be n. Okay, this is the fun part. We're taking logs here, but conveniently this was doubly exponential, growing, the x over b. So when we sum these singly exponential. So it's a geometric series. And so we are just dominated by the last term, which is where we get log base m over b of n over b. And this is our amortized cost per insertion. Deletions are basically the same. You just do pulls instead of pushes. And you have sort of the reverse of a distribution step. In some ways, even simpler. You don't have to do this clever analysis. Question?
Can you explain again, how is it that you got to the distributed cost of x over b? Like the x. So I understand that every time you need to pay the x to the 1/2 because you need to load.
Yeah.
But where did the x over b come?
This is essentially amortized per element. We're just paying 1 over b. Once the block has been loaded, it's only after we insert b items that we have to load another item. So that's why it's x over b here. Good. Question?
Which buffers do you keep sorted at all times?
So which buffer?
Which buffers do you keep sorted?
We're only going to keep the very bottom buffers sorted at all times. So, I mean, it doesn't really matter. You don't even have to keep those sorted because you can afford to look at all of them.
And then I think the upper levels when we're trying to figure out where it goes.
What we do need, we don't need them in sorted order, but we need to know where the max is. Yeah, so I guess maybe maintain a linked list of the items would be one way to do it. So the sorted order is in there, but they're not physically stored in sorted order. That would be a little bit too much to hope for, I think. Yeah, so we do need to keep track of the max, but that's easy to do as you're inserting. Cool. So that's priority queues. You can look at the notes for deletions.